today we're going to characterize an output transformer. So I have here a Champ output transformer, and we've got it hooked into a signal generator and an oscilloscope, and what we're going to do is characterize it for its impedance, and we're also going to characterize it for its turns ratio, and then we're going to look at frequency response. So just a quick recap on the transformer itself. We have, it's two sets of windings essentially, and an iron core. The more iron you have, the better frequency response the transformer will have. We're connected to brown and red on the oscilloscope side, and yellow and black on the signal generator side. And we're injecting a signal from the high impedance output of the signal generator, and then we have a 4 ohm load here, just there. And what we want to do, so when we have these two in parallel, high impedance and 4 ohms is going to equal approximately 4 ohms, and we want to reflect that impedance over to the primary side, because fundamentally how a tube amp works, it's not the impedance on this side that's reflected over here, it's the impedance that's reflected from this side over here. So we're kind of doing it in reverse. We're putting the signal in here, and we're monitoring what the signal will look like. Obviously in an amplifier the signal would go in this direction, so you'd have a high voltage signal here and a low voltage signal here to drive the speaker with a higher current drive. But in this case we're putting the signal in this way, and it's going to be a few hundred millivolts in here, and it's going to be amplified to around 20 volts, and we'll see that when we do the measurements. Let's take a look at what we've got on the oscilloscope. So the blue waveform is the signal that comes directly out of the signal generator, and that has an impedance of 4 ohms, and then that signal is reflected through to the primary side of the transformer, and that's the brown and the red wires that we talked about. And you can see on the blue side here, I don't know if you can see it, but that's about 400 millivolts, sorry, 100 millivolts. So that signal is 400 millivolts on the input across 4 ohms. And then I measured this on the output, and it's around 15.2 volts. So we have a ratio essentially of 400 millivolts or 0.4 volts to 15.2 volts. So let's do some calculations around those two numbers. 15.2 divided by 0.4 is 34.5. So our ratio, just approximately, of windings is going to be 34, let's just call it 35 to 1. Now let's look at impedance. So the impedance is actually this number squared. So I would square 35 and then multiply that by 4. 35 squared equals 1225. So if we've got 4 ohms as our secondary impedance, then we multiply that by 1225, and that equals 5 kilo ohms. So that is the load that will be presented to the tube. So let's eyeball the frequency response. Maybe we'll do a plot later, but we're at 1 kilohertz, so we measured 15.2. So the two yellow lines, horizontal yellow lines, represent a voltage swing of 15.2 volts. So let's increase the frequency. So we're going up a kilohertz at a time, and you can see the signal is getting it is larger. So this, let me adjust the time base. Yeah, you can see it's exceeding the two horizontal cursor lines. We're probably up at about 17 volts now. So it's got a good high frequency response. Let's take it lower in frequency. So we're just winding down the signal generator back to a kilohertz, where it'll match the lines, and then we want to mess with the time base a little bit, because we're going to go really lower in frequency. So now we're scaling down through the hundreds, of hertz. That's 100 hertz there. So we can see roll off has started at 100 hertz. It's just below the two horizontal cursor lines. So let's go down to 90, 80, 70, 60 hertz, and this is kind of where your guitar is going to have its low E note, and then we'll go beyond that, really down, lower in frequency. And as we get down to around 10 hertz, you know, we can see there's a significant roll off. And if we looked at that on a frequency response curve, and it would be in a logarithmic plot, unlike the linear plot that we have now, you'd see a decent roll off. But it's not really going to affect much of the low frequency. It's just the time base again. It's not going to affect a lot of the low frequency response, as this thing's rolling off way below where our guitar would perform, like the lowest E string. So maybe for a bass it's not going to be good, but for a little transformer like this that's designed for a 5-watt amplifier, I don't think I'd like to put a bass in it. It wouldn't last long. Well, the speaker wouldn't last that long, maybe. Well, if you played it quietly, it would be fine. Okay, back up to a kilohertz, just the time base again. And we're back up to hitting the horizontal cursor lines. Let's recap. So we have a signal generator over here. Right now it's putting out a kilohertz. It's a high impedance output that goes across this 4 ohm resistor, which means we're actually reflecting 4 ohms from the secondary winding over to the primary winding of the transformer. The input signal across the 4 ohms was 0.4 or 400 millivolts, and we measured on the oscilloscope 15.2 volts. And so if we divide those together, we get about 34.5, and I just approximated that to a 35-to-1 ratio of between voltage here and voltage there. If we square that so we can work out the impedance ratio, we get 12225, 1225, and so if we multiply 1225 by 4 ohms, we get 5,000 ohms, which is the specification. And then you saw that I winded down the frequency, and we saw there was a roll off around 100 or 100 hertz. I suspected this output transformer on this Champion 600 may be faulty, so I've done the same kind of setup. So this is speaker output, so I've got the signal generator connected to it across a 4 ohm load, and then I have the oscilloscope connected via pin 3 on the tube, so there's no tube in, so I'm just essentially measuring the signal generator, and it looks like I've got 20 volts of signal versus 400 millivolts in. So let me do the calculations on that. We measure 18 volts on the output, put 400 millivolts in, divide those two together, that's 45, so essentially it's a 45-to-1 turns ratio. Square 45 equals 2025, multiply 2025 by 4, which is the load that we've got on the amplifier, equals 8K, which would be an appropriate impedance for the type of tube this amplifier has. If we take a look at the specifications for a 6v6, which is what's recommended in one of these little amplifiers, 5-watt amplifier, there's a 6v6 tube. For around 300 volts of plate voltage, you need to be at about 8,000. Some forums say you can go down to 5,000. The new transformer I bought actually has a 5,000 tap and an 8,000 tap, as well as a 4 and 8 ohm load. So that's a fantastic transformer that I got from CE Distribution. And so this transformer actually looks to be working fine. I've run a few frequency response tests on it. So where I thought it might have been the output transformer, it could be the tube. So I'm going to try and check the tube on a tube tester for this amp, but I know I'm happy with the performance of the output transformer in this Champion 600. Again, we've learned today that if we present a voltage across 4 ohms on the primary side, the secondary side of the transformer, it'll reflect to either 8,000 or 5,000 ohms on the secondary side. which is going to be a good load impedance for a tube like a 6V6, which is used in some of the Fender Champ amplifiers, single-ended, I just like to point out as well, not a push-pull. So it's a Class A design that we're using with the Fender Champ and the Fender Champion 600. So everything seems to work out. We've characterized this one. We've also verified that the transformer in the Champion 600 that I'm modifying is also good. So thanks a lot. Please don't forget to like and subscribe, and I'll see you in the next video.